Hello, my name is Josh Matthew, and this is my presentation of homework number 7. So, in this homework, we are asked to modify the heat conduction MATLAB code we previously used in homework number 5, and we're asked to modify it and make it a time-dependent solution for the temperature distribution as given in the homework. So, shown here is my modified MATLAB code that I used. I decided to divide it into 3 different parts. So in part 1, the code is going to prompt the user to enter consistent or lumped. So 1 equals consistent and 2 equals lumped. And the next one would be prompting the user to enter the number of finite elements. In part 2, this is going to prompt the user for the rest of the remaining inputs, such as the initial temperature, the delta T, the total time, etc., and also the activation time for the heat source. And in this part, I'm going to combine the first 2 functions, and I'm going to call them right here. And so when you run this MATLAB code, it is going to prompt the user a bunch of questions, and this here is my screen output after running the MATLAB code. So as you can see, the values that I inputted. So the goal here is to select or obtain simulation parameters that give us stable and physically realistic solution results. So this would mean non-oscillatory. And then we're also asked to print out a plot of the plots of the transient temperature distribution at the initial time, halfway to the total time, and also the total time. So right here is my temperature distribution at the initial time t equals 0. So here the observed profile matched my expectations since the rod started at an initial temperature of 50 and began heating up throughout. This here is my temperature distribution at half the time, and that is at t equals 5 seconds. So here are the 4 different sections, and the material properties of each one leads to faster temperature rises in certain areas. The second section from around x equals 0.6 to approximately x equals 1.3, we can see that it heats up faster than the rest of the rod because of Q equals 1000 watts per meter applied to that section. This is the temperature, this is the third plot, and this is the temperature distribution that I obtained when the heat sink is activated, and that will be at t equals 7 seconds. So here the rod is still heating up as it should, and from t equals 7 seconds to 10 seconds, that's when the heat sink is supposed to be activated. This is the 4th plot that I have, and this is the temperature distribution at total time t equals 10 seconds. This final profile also matches my expectations. So after t equals 7 seconds, the heat sink is activated and the rod starts losing heat at that specific node around x equals 1.4. So again, this is my screen output after running the MATLAB code. And for part 3, this is my answer. We're asked if it is possible to replicate a steady-state solution with the time-dependent solution. And I answered yes, it is possible to replicate a steady-state solution with my time-dependent solution. So when we change the location and value of the heat source, we will notice that the temperature distribution begins to look very similar to the steady-state solution. We can also do this by changing parameters such as lambda, theta, and the total time values, and we can get the time-dependent solution even closer to the steady-state solution. Apologize for that sound, my cat just jumped on my computer. Once again, thank you very much for listening to me. I hope you all have a great day. Thank you.